Thank you. Good morning. I'm ready to answer questions about yesterday's lectures. However, I'd like to start with a very brief summary of what we did yesterday. And yesterday, our task was, after a general introduction, just to find out what the general equations for Markovian open quantum systems are. And our task today will be to try to see in some examples how we can get intuition about what these equations mean and contain and predict. So, very briefly, this is something you all know for years. What happens for isolated systems? You have a certain task which is in the realm of physics, which is to find the right unitary evolution. And I recall that this is unitary. And then we are in discrete time. To compute the evolution of the system, you just have to iterate the map that rho gives you rho UDAG. And so you start from rho 0, rho 1, rho 2, and go on. And that's computing things. And of course, it's a good idea to diagonalize U to make this evolution simpler. But apart from that, this is basically the content of quantum mechanics apart from measurement. And now what we saw yesterday is that if you have an open system, your task is more complicated. Even if the universe has a unitary evolution, when you look at the what happens at the level of the system you're interested in, you have to find operators AA. They are not unitary. There are a number of them, an arbitrary number, but they satisfy some constraint. And this constraint is just that when you sum over AA, DAG, AA, you get 1. Of course, if you manage to describe your systems with only one A, I'm saying again that it's going to be unitary, and everything, this trace will be 1 and all that. So if there is only one A, this means in fact your system is isolated and not open. But if you have you have to find a bunch of A's, and of course, well, we have developed recipes to know how to find the appropriate U for many systems. I mean, we take the sum of the kinetic and the potential energy to get the Hamiltonian, and then we take the exponential to get U for a unit time and all that. So, and for spin systems in the magnetic field, I mean, there are many instances in which we have intuition or we have learned what's the right U. For open quantum systems, the situation is much more complicated, and it's a non-trivial task in general to decide what is the appropriate set of A's to describe the system. That's something that doesn't come for free. But if you forget about that, you imagine that God has given you a certain solution of this equation, then your task is the following. God gives you two things. He gives you a certain set of A's, and he also tells you that in fact you are in trouble to discriminate them very precisely. You are only able to discriminate whether A is in some subset of S and not as an individual, and then you have just to iterate this map, which is something you can easily do on a computer as long as you don't have too many matrices and you don't have too large matrices. Then this is very easy to put on a computer. And the main difference when you go from here to there is that in general what you get is you have to iterate a dynamical system, which is a random dynamical systems, which means that at each time step you have to make some choices, probabilistic choices. So the first thing to do is to compute these numbers and then to choose one of the possibilities with the right probability, and then when this comes out, you compute this to get the new density matrix, and again you iterate. And there are two special cases which are important. The first one is in fact when you do not look at all at the result of the measurement. You measure, but you don't look at the result. So you have a totally fuzzy reading of the measurement. And then what you have to do is to iterate this map. And this is really what a partial trace would give you. And the other extreme is you are able to do the measurement and to read it accurately. And so then, in fact, all these guys here are singletons. And then you have to choose precisely one A. You choose it with that probability and you iterate this map. And the little miracle that I was unable to explain yesterday, and of course it's just so simple and whatever, is that now if for any of these equations, if you take the probabilistic expectation of rho prime, this is rho prime, you take this probabilistic expectation, you see that what does it mean? You take each possibility and you weight it by its probability, and when you do that, these guys cancel, of course, and then what you find is that here you get that the expectation, this is probabilistic. This is, I take the standard notation for expectations. It's an average if you want. It's exactly going to give what a partial trace would have given to you. So this is in essence what explains that by doing measurements and not looking at the result, you can do exactly the same thing as taking a partial trace, which is what amounts to have an interaction with an environment over which you trace. Okay, so this is the main reason why having a system in contact with an environment or having a system on which you make measurements is essentially the same thing. Okay, so this is, if you take this home with you as a take-home message, then everything is perfect. So now I think it's an appropriate point if you have questions about yesterday's lectures before I go on for the program of today. Everything crystal clear or everything too obscure? These are the two options. Anyway, so again, I would like to say, if you like to do some computer simulations, it's very easy to simulate these things, and you could do it, have some fun with it. And now, today, we are going to give a few examples of AAs and see what they yield. Okay, so I can erase all this, no regrets, for good or bad. This is the end. So this equation here that I could even put to keep on the screen, because these are really the equations we shall use all the time, so it's good to have them somewhere to remember. So today I would like to do two different things. So the aim today's lecture is to give a few examples of family AIs, and in particular we shall go to these so-called non-demolition measurements. This is one of the single cases I know of where you can really can take your a few pieces of paper and work out the solution of what is going on in a very detailed and precise way. And the second aim is to explain the continuous time limit it's independent of non-demolition measurements, and the partial trace or the stochastic. If you take the partial trace, there is no probability remaining anymore, and this leads to rather simple equations. And if you don't take the partial trace, you have to take into account that at each time step you make a random choice, and then at the end you get stochastic equations that are quite similar to stochastic equations you can see in other instances of physics. Okay, so the first, so I will give two examples. So before going to non-demolition measurements, I will give the simplest example, which in fact is not so clearly the simplest to analyze, but at least it's easy to understand, to formulate at least. And it's what I would call random unitary evolution. And what is it? It's, you imagine that you have a family UI, a family of unitary operators, that act on the system. By the way, I forgot on this blackboard, I forgot to put the little index S to the density matrix, but that's okay. That's when we only talk about the systems, there is no point in carrying this subscript all the time. So okay, so I take a family of unitary of HS, and I get that PA, a probability measure with the same index set. So PA is larger than 0, and sum over A of PA is equal to 1. And then claim, which is obvious, AA, that I take by definition to be square root of PI UI. I claim this satisfies the defining equations. Sum over A dag AA is equal to the identity on HS, and the kind of evolution you find. So let's concentrate on the two extreme cases. Just so you have one which is simply to map rho to sum of A PA UA rho UA dagger, and the other one which is to map rho to UA rho UA with probability PI. PA. Okay, so what I claim is, so these operators satisfy this, and if you take these guys and you plug them in the equations, what you will find is that in fact, if you take the case that you don't look at all at the result of the measurement, or if you do it using a partial trace, this is the same, I insist on that, then the map is the following, this one, and if you really look at the result of the measurement, then it's just rho gives you a rho UA dag with a certain probability PA. So in that case, you see, this is really random unitary evolution. So at each time step, you just have a dice or something like that, some device that you throw independently of what happened before. It gives result A with a certain probability PA, which doesn't depend on anything. So it's really a dice or a coin if you don't if you have only two A's. And if it's PA, then you decide that the evolution for the next time step is going to be UA rho UA dag. Okay. And now if you make the average, you have to make this sum. And okay, so this is something which is relatively easy to analyze in some cases, but it's already relatively tricky. Of course, if the UAs all commute with each other, then it's very easy to do things in a simple way. I let you check that then you diagonalize them simultaneously, and because they commute, everything at large times, everything will be described by some law of large numbers, let's say. So this is very easy in that case. However, if you look, and if they commute, well, yes, there is not much mystery. However, if they don't commute, then you are looking at products of random matrices, which appear in many branches of physics. They appear in condensed matter. In condensed matter, the U's would not be unitary in general, but you have disordered systems. They wouldn't be unitary, but it's just iteration of such maps. And well, this is not so easy to understand in general. But again, you can do numerical simulations and see what this yields. And this case is quite interesting. You see, from a certain point of view, this is a random unitary evolution. However, as soon as you have, so it's always unitary. However, as soon as you take the averages, this is not a unitary evolution anymore. And so rho, for instance, shows certain features typical of open systems. And well, you might, for instance, try to find what are the fixed points for this evolution and all that, and see what it yields. It seems pretty obvious. I never thought about it, but for instance, it's pretty obvious that rho is 1 over dim HS times the identity on HS is a fixed point for this evolution. So you see, if under some non-degeneracy circumstances, in fact, if you iterate this, in the end, what you will find is the totally diagonal density matrix. So even if rho describes the pure state to start with, in the end, it describes the completely uniform mixture of states. Okay, so which is a typical effect of open quantum systems. You start with something which may be in a pure state, but because you interact with the environment, little by little, you lose coherence in your matrix elements, and in the end, what you get is something incoherent, and in that case, it's just a very simple statistical ensemble. Okay. So this is the first example, and again, if you like to put things on a computer, just feel free to do it. And I would now like to go to what will occupy us for quite a long time, which is non-demolition measurements. And maybe it's appropriate to start with an experiment to describe. And again, as I showed you already yesterday, the one I have in mind is this experiment done at the École Normale, and then I will explain how to compute the Hamiltonian for this and do precisely all the exercises. And let's go. So I want to recall something from yesterday, that in fact on H, which is equal to H system tensor HE, we decided that HE could be taken as some kind of tensor product, let's say 1, 2, etc. We had a reference state, but this is not so important. This is HE, and we defined operators U n acting on H, I'm sorry, this is H system. H system tensors the nth copy of K, so K. So each probe has its own Hilbert space K, and we have an operator acting on HS only on the nth probe. And so essentially, and in this picture, you see there is one atom inside the cavity. So basically, the evolution, you see these guys, they have not entered in interaction with the magnetic field, so nothing happens to them. These ones have left the cavity, so nothing happens to them, and only this one is interacting with the cavity. So it's exactly this. If this is the nth probe, we just have to apply the UN, which is acting on the nth probe. Okay? And non-demolition is when the UNs commute among each other. And this is a definition. I mean, I will explain why this is a reasonable definition, but this is a definition. We say that with the experiment we are doing is a non-demolition experiment if the UNs commute. Okay, and then there is a little lemma, which is the following, and I will not give a proof because it's a bit long, and but it's interesting, and I invite you to think about it. So there is a lemma. If you don't find the proof and you're interested in the proof, then come and ask me for the solution. Lemma, the UNs commute if and only if there is an orthonormal basis alpha of HS such that U can be written as sum over alpha tensor U alpha, where U alpha is an unitary on K. Okay, this is the lemma. So you see, this is some kind of abstract definition. It's acting, and this one is acting as U. Okay. This is a definition. It's an abstract definition. It's general. It's conceptual somehow. We are stating that a certain number of operators, they commute among each other. And in fact, as happens often with commuting operators, there is a little lemma that guarantees that in some sense you can diagonalize these operators simultaneously. This is the message. Okay, and it's not a very difficult lemma. I mean, you have to think about it and use the theorems you know in quantum mechanics. Okay, so this is the result, and now we would like to analyze it. And for instance, once you've got this formula, for instance, we would get so U1. Imagine now that I take only just two probes, just to illustrate. And so U1 would be equal to sum over alpha tensor U alpha tensor the identity on K. U2 would be sum over alpha tensor identity on K tensor U alpha. And now if you make the product, if you want to get the unitary evolution for 2 time steps, then what you would get is that the 2 time steps evolution, which would be U2, U1, it's a one-line computation to check that this is just sum over alpha of alpha tensor U alpha tensor U alpha. And if you would do it in the other way around, you would find the same result. So indeed, it's trivial to see that if you have such a formula, indeed, all the UNs, they commute among each other. This is the 2 time steps evolution. Okay, and you could generalize to more probes. But it's obvious that this is going to work. And now we need some vocabulary. The alphas are called pointer states for the evolution. And the name comes from if rho S is equal to some, let's say, alpha, check, this is for you. rho s is fixed by the evolution. By this I mean you start in a pointer state, you apply the rules that I gave you to compute the evolution, and you do the partial trace, and you see that this guy here is going to be invariant. Maybe I should call it alpha 0. I choose one special pointer state, I start in it, and it's fixed by the evolution. And in that sense, this is called non-demolition in the basis alpha, in the pointer states basis, because indeed, if I start in this, whatever I do, even if there is a tendency to scramble everything with the unitary, with the evolution and the partial trace, for these special states, they are not scrambled, they remain what they are forever. Okay. So now that we have this little vocabulary and explain why these states are important, we can go to analyze. As you can see, I have not yet talked about measurement at all, in fact. There is no measurement on this side. So now I should have a look at what the operators AA are in this situation. So I am going to do a measurement. So what am I going to erase? Maybe I'm going to erase this. And that. So now we have something. I will explain how it goes for this precise experiment, but now we have a formalism that explains what happens here when the probe come by one, and the next aim is to describe what happens next, which is that after a while these guys are measured. Okay. And so now we talk about measurement. And then we choose an observable. We choose a complete observable on H, on K, I'm sorry. The observable, it's on K. Oops, I'm going to get it. And so let's say it's sum over A, lambda A, PA, and it's a complete observable, means that these are 1D projectors. And these guys are distinct. So this is a measurement that allows me to define a one-dimensional subspace of the probe space. Okay, so these are what I call complete. And then you write down the equations and you compute the AIs, and this is what we want to compute. And in the pointer state basis, it's very easy to compute that in fact alpha AI beta is nothing but delta alpha beta times alpha AA psi. And remember, psi, as usual, this is the initial state of the probe. Again, all these guys here, they arrive. In fact, this is used to do that. You create this, you emit these guys, you put them in the appropriate state at this position, and this state is just psi. And so what the answer is that, well, no, that's not, I'm sorry. I'm sorry. This is completely wrong. I don't know why this is. So psi is correct. Here is U alpha. And here is the state A. PA is just the projector on A. I'm sorry. This is the correct equation. So when the matrix elements of this guy here are just, it's diagonal. So AI in the pointer state basis is diagonal. And by definition, I give a name to this, and so alpha AA beta. To have a slightly shorter notation, it's just delta alpha beta, and then I introduce a number, and this is denomination, and I put here a bar, and this is not a scalar product or whatever. I mean, this is to remember that this is related to conditional probabilities, as we shall see later. Somehow, you can see this as an amplitude to find A, knowing that you are in pointer states alpha. So this is some kind of conditional probability. But at the moment, this is not just a notation. This is just by definition equal to what you get when you get A U alpha psi. Okay. So now you can go on and write things in the pointer state basis, and it's very easy to get the evolution for rho. Oops. Okay, okay, so if you allow me, this will simplify my task. I'm talking only about the system from now on, so I don't put the subscript S. And I go to the pointer state basis. So I have rho alpha beta, which is equal to alpha rho S beta, and I decided I didn't want to keep the S. Okay. And then you just have to write down the equations. So you imagine that you read correctly the measurement outcome. And what do you see then? Well, if you translate just the general equations, what you see is that rho prime alpha beta is going to be rho alpha beta C of A alpha C of A beta bar divided by sum over gamma rho gamma gamma modulus of C of A gamma squared, and this happens with probability sum over gamma of rho gamma gamma modulus of C A gamma squared. This is just an exercise for you. If this is not obvious for you, you just take the general formulae that I gave. You take this precise value for the operators A, and this is what you get. So you see, this is quite remarkable. Apart from the denominator, what you get is that rho prime alpha beta is just proportional to rho alpha beta with a little coefficient. And this little coefficient is just there to ensure the normalization that trace of rho remains equal to 1, in fact. Okay. And remark, sum over A, dag, AA is equal to identity on HS is in fact exactly equivalent to sum over A, C of A alpha modulus squared is equal to 1 for each alpha. Okay, and so it's tempting to define. I'm sorry, I put sometimes a comma and sometimes a bar. Let's put a bar everywhere. So this is this little identity, and so it's tempting to call this P of A knowing alpha. And indeed, interpretation, this is correct to use this denomination. If rho is equal to alpha alpha, and you do the experiment, of course, as I told you, rho is not going to be changed because you are starting in a pointer state, nothing happens, but then P of A alpha is the probability of probe outcome A knowing that we are knowing alpha. So this is a probability indeed. Okay. So in the denominator and in the probabilities, what you get are somehow conditional probabilities. Okay. So now our task, in fact, is to see how we can analyze this random recursion relation. You see? This is reasonably simple, the random recursion relation, and we shall see that we can, in fact, solve it explicitly and understand what is going on. Before doing that, I would like just to explain a little bit in more detail what happens in the experiment. So, okay, we don't have. So, a word. So, about the experiment. So, what do we have? We have a cavity. It's a very high quality cavity. It's basically, I mean, the side of this cavity is, well, basically that size, the size of this little object, or so something like that. Okay. And if you want to know the quality, well, I would have to give you the wavelength of the resonant wavelength, but it's small, and then the quality is enough that nothing happens. I mean, you don't lose photons or things like that for basically 1/10 of a second, or about 1/10 of a second, and which means that a bit more than that, in fact. And during that time, the photons, they have the time to bounce on both of these of the mirrors, and basically they do a round trip around the Earth. The amount of they do basically 40,000 kilometers before anything happens in the cavity. So you imagine the number of times they bounce. It's basically 10 centimeters. So you don't lose photons in the mirror for a very long time. Okay, and now, as I told you, these guys here are Rydberg atoms. So they are atoms in a quite excited state, and they are extremely sensitive to magnetic fields. So you can write down explicitly the Hamiltonian, and I just don't want to make mistakes, so let me find the formulae for what is going on. Oops. Of course, as usual, when I look for something, what I know by heart, and what I look for in the notes, I don't find. It's somewhere, which doesn't help very much. Yes, okay. So, the pointer states, okay. Are those with a fixed number of photon. You see there is only one excited mode in the cavity, and so in that mode you can have an arbitrary number of photons as usual. So the pointer states are just the eigenstates of the photon number operator. And then the interaction is extremely simple. It just tells you, so in an appropriate basis, the unitary operator describing the interaction of one probe with the system is just e to the I theta, let's call it n sigma z, and sigma z is an operator in probe space. Okay, so this is a number operator, and of course it's easy to see that indeed you can write it, you can decompose on the basis of n, so somehow you would exactly have what I told you, which is that you have, this is going to be sum over n, nn, the photon number operator, tensor e to the I theta n sigma z. So this would be what I would call u. Well, this is not a very. Let's say there are there are L photons inside the cavity. Let's call it L, the photon number. And then this would be what I would call UL. This was U alpha before, but there is some kind of clash of notation. But anyway, so this is the way it works. And theta is related. You can change theta to the time spent in the cavity. You'd see if the probes go very quickly through the cavity, theta is small. If they go very slowly in the cavity, theta is large. And so what these guys managed to do is just to choose to adjust theta if I'm correct, it's pi over 4. Okay, so that n is equivalent to n plus 8, in fact. You see, just because nothing happens. And so basically, with this device, the probes, if there are differences, if the number of photon is 1 or 2, the things are not the same. However, if the number of photon is 1 or 9, things are the same. So they just count things modulo 8, but apart from that, this is exactly this formalism, and you can apply it up to the end. So this is, and then when you do the measurement, of course, so you rotate along the axis Z. This is, maybe I should say it once again. These Rydberg atoms, they can be in two different configurations. One which is excited, in fact, it's the 50th level of excitation of the atom, and then one which is the 51st. And so you identify them with the two-level system, and so sigma z is not. It's just this is not because this is coupled to the spin or whatever. It's just because you have a two-level system. And if you have a two-dimensional Hilbert space, you can define operator sigma z. Okay, and then you will measure exactly the same observable, but along another axis to make the measurements. Okay, so this fits in the picture, and so you could take the formula I gave you. You can compute, once you have this, you can compute all these coefficients and all that. You will see that cosine theta is going to play some role, appear in these probabilities and all that. You can do it, and then you can either look at the experimental results, or you can do numerical simulations, and I will come to that very soon. So I go back to the general case. And what is this general case telling me? The first thing is that the diagonal is closed. By this I mean that you can, if you look just at the diagonal components, you never need non-diagonal ones to get into it. And so if I decide that Q alpha is by definition equal to rho alpha alpha. In fact, if I concentrate, so it's the diagonal part, then it's easy to see that the iteration is just going to be q prime alpha is equal to q alpha p a alpha divided by sum over beta q beta p a beta with proba, as usual, the denominator, so sum over beta q beta p of a beta. And so you can have fun trying to iterate this map. So I told you that it was easy to simulate, these systems were easy to simulate numerically. This is even more true here. You don't even have to use complex numbers and whatever. You just iterate a very simple dynamical system. And if you do that, and you start with some kind of, you just take arbitrary probability measures, satisfy, well, arbitrary probability measures, blah, blah, blah. So you simulate, and what you see is the following kind of picture. So you imagine that you have a system with 7 states. This is this numerical simulation. You have a system with 7 states, and you have a certain starting point. Some of them you barely see. I mean, there is one that disappears quickly, but you start somewhere with certain values of these guys, and you iterate. And so this is the picture, and so you iterate once, twice, blah, 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 and up to 600 times. And what you see is that you see rather strong fluctuations, but in fact, in the end, things turn out to be extremely simple. All but one of them is going to decay exponentially, and one of them is going to go exponentially fast to 1. Okay? And this means that whatever the initial state you take, all but one of the states will completely disappear, and one of them will emerge in the end of the simulation. And if you look at the pictures given by the authors for the paper, it's exactly what they see also in the experiment. This is what they do in the experiment. I will explain a little bit how these things are got in the end, but they have these photon numbers modulo 7, and they start in a certain, they start in fact with the uniform distribution for the photon number, and they look at what happens when they make measurements, and little by little what they find is that indeed all the photon numbers seem to go to 0 but 1, and however deciding which one goes to 0, which one goes to 1 is not so easy. Here you could imagine that this one is going to win, but in fact it's that one that wins. And in another experiment, exactly the same experiment, same initial condition, but different probe outcomes. In fact, the one that wins is the one with 7 photons. Here it was the one with 5 photons. So what they observed in the experiment was what they called progressive field collapse. Indeed, progressively, what you exactly see, the collapse of the wave function, going from a wave function that is describes a superposition or a statistical ensemble. It depends. I mean, it doesn't make any difference here. Either a quantum superposition or a classical ensemble. And little by little, it gets to a collapse to a single photon number. Okay? And however, which photon number is selected at the end of the experiment depends on the experiment. So it's not exactly like with the law of large numbers. You know that, you probably know that at some point you find a certain frequency. I mean, you throw your coin or whatever, and in the end, the mean frequency is going to converge to something which is basically 1/2 if the coin is fair, or another value if the coin is not totally fair. But it's always you always go to the same value, and whichever experiment you do, you go to the same value, which is essentially a measure of the fairness of the coin. Here, you go to something, but this thing is random. It depends on the experiment. Yes? Yes, I can. I can, however, I have to look in my notes. I will give it at the I'll take it during the pause, and I'll give it. Yeah. Okay. So this is what they observe, and just to say, so this picture seems to be, well, of course, they have nicer, they make nicer pictures in the article than I can do on my computer, but basically you see basically the same thing happening here, that this guy, you think it's going to win, but maybe it's not going to win, it's this one, but in the end, it's this one that wins. Okay. Exactly. This is they call it progressive collapse of the wave function. And this raises a certain number of questions, so that's what they see in the experiment. And what I would like to convince you in just a few minutes, very quickly, is that indeed, that's exactly what is predicted by these random recursion relations. These random recursion relations, they predict that in the end you have the collapse of the wave function, and they predict, in fact, more, which wasn't known to the guys doing the experiment, which you may think is obvious, but nevertheless you can prove it. So these predict that the wave function collapses, and in fact it collapses in exactly such a way that the final result is exactly the result of the standard measurement. So if you start with certain, if my starting point gives some weight to let's say I have Q1, Q blah 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 up to Q7, then if I start with a certain special point here, well, the probability to end up in state 7 is just equal to Q7. The probability to end in state 5 is Q5 and all that. So these experiments, these non-demolition measurements, they are just a way to progressively make a standard von Neumann measurement, so that contrarily to what, standard von Neumann measurements, they are supposed to be instantaneous, and so you have something before, something after, and you have no idea what happens in between. These are really devices that allow you to have something totally unexpected, which is to really see what happens if you do the measurement progressively and to see things happen really little by little. It's just as if you could say, okay, there was this idea from the beginning of quantum mechanics that the measurement apparatus has to be macroscopic to have the wave function collapse, but of course it's not possible to do it when you cannot start the wave function collapse with one apparatus and say, okay, now I will do it with a slightly larger apparatus and all that. Here it's really a device that allows you to monitor very nicely to see things happen little by little progressively. Okay, so now let me try to explain. Well, maybe it's an appropriate point, in fact, to make the pause, isn't it? What do you think? Okay, so we resume afterwards. Yes, welcome. No. Yes. And we started to iterate that, then you really would not expect that, say not 100 but 200, where the yellow line is above the green line. We would not expect that the green wins over the yellow, right? No, but it does. Well, in that experiment it does. In another one it won't. So it sort of looks like to me that there are sort of memory effects involved, but I mean. No, because it's really Markovian, so there are no memory effects. And in fact, you see, if it would be extremely puzzling, in fact, what happens, okay, just to say it so, okay, here, this black here, if I'm correct, let's say at this point, let's say it's 0.3, then this guy he has 0.3, the probability 0.3 to be the winner at the end. Well, it is not. And then if I start anytime here, if I give you this configuration, but well, again, you would expect that this one here has exactly 0.5 probability to win, and this one has 0.35 or something like that. No memory effect. And in fact, this is the incredible thing. It's a random evolution, but it converges in a nice way. Okay. No, but it's okay. But okay, so you have this U, and from U, if I tell you that you have to how to compute the AAs, you will do it. Okay, so AA. So this is going to be UL. So you will have certain AA. In that case, they will be A. Okay, they will be AA. A is going typically to be plus or minus because these are two-level systems. I will make the measurement on the two-level system, and AA. It will have components L m, let's say, and if you do the computation, you will see that it's delta Lm times something which is, if I'm correct now, A UL psi. So what I didn't tell you exactly is what the A's were, but I can tell you I'm just measuring along sigma y, let's say. I make the measurements along sigma y in the probe space, and I have to tell you what psi is. Well, take whatever psi you want. And you compute it, and you will see, well, just by this condition that this decomposition holds of sum, the AAs are going to be diagonal, and with certain coefficients, you can go up to the end and express it in terms of theta. And if you take, well, be simple. I mean, let's say takes the psi's to be, let's take psi to be that it's pointing in the plus x direction, let's say, to start with, and measure along the y direction, do the computation, and Does that answer your question? Okay. Well, if no more questions. I made a mistake. Okay, just. Okay, so now I would like very briefly to outline how we can understand these results, starting from these equations in general, and we shall in fact concentrate on these ones, but there is a similar discussion that can be done there. Okay, so here I indicated the reference. That was a fair question to ask what the reference was. But in fact, well, it's at the same time fair and unfair, because this is the experiment I understand the best, but many other people have done similar experiments with similar results now. And you can do this in circuit QED and not cavity QED. You can do it, well, there are many ways to do it. Okay. And again, one of the beautiful things in this experiment is that you see the progressive field collapse, and the other one, which is just truly remarkable, I already discussed that a little bit with two of you yesterday, is that, you know, measuring photons is easy. Measuring photons without destroying them is difficult. So usually when you measure a photon, it enters your eye, it excites some electron, and the photon is gone. You can measure it, you can decide, your eye can decide if it's a red one or a blue one or whatever, but once you know it's blue, it's gone forever. In this experiment, at the end of the experiment tells you there are 5 photons in the cavity, and indeed, the 5 photons are still in the cavity, and you can still manipulate them and do something with them, which is truly amazing, I mean, if you think about it. Okay, so now for the explanation. So I will offer 3 explanations, and without details, and because these explanations, they all rest on some probability theory that is maybe not familiar to all of you. So I don't want, well, it's not very difficult, but I don't want to enter that too much. So first discussion. So point 1 is Bayes' rule. And I claim the following, that this is exactly, this relation star is exactly Bayes' update rule. Is Bayes' update rule. So what is who in the audience is familiar with Bayesian statistics and these things? Okay, at least a few of you. Okay, so you probably know more than me on that. But okay, so imagine that you've completely forget about the problem we have at hand, which is quantum mechanics, and you have the following. You want to decide if in some experiment you make some experiment which can have outcome either alpha 1 or alpha 2 or blah blah blah, and you get information on some other thing, and you just know conditional probabilities. So what you are aware of is that you know the probability that, so you have this experiment that has given a certain result, which say can be alpha or beta or blah blah blah, and then you get partial information by telling you that in fact what you find in another experiment measuring something else is A, and you know these conditional probabilities, and you have some a priori estimate of what is the probability that the initial experiment gave result alpha. And then I give you I say, okay, so you think that the original experiment gave alpha with probability Q alpha, which is in your mind, but I give you some information. I tell you that I made some other measurement and it gave A. And then how do you update your knowledge? So for instance, I don't know, you think there are some correlations between the fact that you're a man or a woman and you smoke or you don't smoke, and you tell me, okay, I've chosen a person at random and you have to decide if it's a man or a woman. And well, if I do statistics over the world, there are a bit more women than men, and so I decide that let's be it's points 43 that it's a woman and 53 and 47, and then somebody says me, okay, but then I checked and this person smokes, and then I know that men are more smoking than women. At least that was true a few decades ago, but I'm an old man. So I have to decide what is my new probability. How do I estimate if the person chosen was a man or a woman? And this is the way I am going to update it. This is exactly what I'm going to do. Okay, and so as you may believe, if I give you many partial informations like that, in the end, even if your initial guess was not correct, little by little, by gaining information, you will end up with the correct guess in the end, after you've collected many information. Okay, so this is and in fact, okay, so this is a way to convince yourself. Of course, you don't know exactly what you don't know exactly what is going on in the process, but in the end it's going to converge. So one of the reasons for convergence is exactly Bayes' rule. This may not be too convincing, so let's give a second condition for convergence. It's in fact related to the first one, and it's related to probability theory. Let me compute what is the expectation of Q prime alpha. Okay, so again, this is one of the main messages of the lectures. Denominators cancel with probabilities, and let's do the computation in full. So this is going to be sum over A, Q alpha, P of A alpha divided by sum over beta, Q beta, P of A beta. This is my observable times its probability. So this is sum over beta, Q beta, P of A beta. This cancels with that. And now I have to sum over A, but this is a probability distribution, as I mentioned. And so this is going to be Q alpha sum over A, P A alpha. And this is going to be just Q alpha. Okay? So this is a remarkable probabilistic property, that this iteration rule, in fact, preserves expectations. So if you know everything up to a certain time, and you know that you had, at that time, you had Q alpha, then you expect, your best guess for what will be next in average is exactly Q alpha. And this in probability theory is called the martingale. This is just a name, you don't have to be convinced. And if you would do the computation for non-diagonal coefficients, you would see that the expectation of rho, you do the same computation, use the Cauchy-Schwarz inequality, and you will see that the expectation of rho alpha beta absolute value is smaller than or equal to rho alpha beta. And then the probabilists would call this a super martingale. Okay, and in fact, so now you open a probability book and you find among the deep theorems of probability theory that martingales and super martingales, they have a very strong tendency to be convergent. So this is a deep generalization of the law of large numbers, and what it's telling you is that indeed these things are going to converge. And you see, for this one, it has to converge in such a way to preserve this identity, and for this one you have a decrease. So if you so they will converge. So let me explain this with just epsilon more details. So now you have to make a technical hypothesis. which is the following. The probability measures P of something knowing alpha are different for different alphas. Okay, so these are conditional probabilities that the experiment gives result A knowing that you are in the pointer state alpha. So imagine what would happen if for different pointer states you would have exactly the same conditional probability. Well, of course, you wouldn't be, of course, you don't expect you will be able to discriminate between alpha and beta if P alpha and P beta are the same probability measures, because when you will update, you will just see how can you discriminate. There is nothing in your knowledge. When you gain knowledge, it doesn't allow you to discriminate at all. So a necessary condition if you want things to turn out nicely is that these guys are different. And then theorem, which is, let's say, super martingale convergence theorem if you want. Is that with probability 1, so which means unconditionally, the iteration converges, and so rho alpha beta converges to 0 for alpha different from beta. So this is the non-diagonal elements. So very naively, I mean, you see, you can have this of course, this martingale convergence theorem is, as I tell you, it's a generalization of the law of large numbers. It's really non-trivial. However, you can have some idea of what is going on here. Look, this, in fact, is decreasing, and in fact, if I now add the technical hypothesis, in fact, you use the Cauchy-Schwarz inequality. If I add the technical hypothesis, then in fact, you will even have a strict inequality in expectation. And so in expectation, and you can even put a coefficient here saying that, let's say this guy is only at most 90% of that guy. I mean, depending on these guys here, Cauchy-Schwarz, blah, 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 you can put really, you say that you will really be decreasing in expectation. Well, then at some point you expect that you will go to 0. I mean, but it requires a real proof. I mean, it's not so obvious, but intuitively this is clear. And for those ones, it's a bit more complicated because it doesn't. It's exactly. It tells you that these things are equal. So what is going to happen? It's harder, but anyway. So and Q alpha will converge when you iterate. It will converge to something. So I should maybe add a subscript n. This is the nth iterate, and Q alpha o n. I imagine we will tend to some Q alpha infinity. And in fact, because of this expectation, you immediately see something that is related to measurement à la von Neumann. This is going to tell you that in fact, the expectation of Q alpha infinity is just equal to Q alpha n for any n. I'm sorry, Q alpha 0. Because you see, after the first step, the expectation, you take first step, you have Q alpha 0, then you would average over the second step, but you do it in succession, you again get Q alpha 0 and so on. And so the expectation of what you end up with at infinity is just Q alpha 0. It goes little by little. And now, what is non-trivial still with this supermartingale convergence theorem is in fact, because these probabilities are different, you don't need for this theorem, because the technical hypothesis well, in fact, Q alpha infinity is just equal to some delta alpha gamma. Okay, so this is it. This object here is still a random object. this here, I'm sorry, I should write it in a larger, it deserves a large place. It's that, in fact, because of the technical hypothesis, Q alpha infinity is always 1 or 0, and it's going to be delta alpha gamma, where this is still a random object. To get this, you have to have a bit more than the theorem, but this is exactly telling you that, okay, and again, what is going on? As I told you, the pointer states are fixed point of the recursion relation. So if you start with a point in a pointer state, you will remain in it forever. Now, it turns out that you have to think about it, because being a fixed point for a random thing is not exactly being a fixed point for... You could imagine that things that are not strictly fixed points for the deterministic stuff are fixed point for the random stuff. What you have to convince you is that this doesn't happen in this situation. So the only fixed points, in fact, in this situation are the pointer states. And as you converge, you have to converge to a fixed point of the transformation. And then, because the pointer states are only the only fixed points, you have to converge to a pointer states. Okay, so this is a pointer state gamma. Okay. And if you put together this and that, well, this is exactly telling you that at infinity, you end up in pointer state gamma with a probability which is equal to a q of gamma 0. Yeah. Okay, so the moral of this is that whatever you do, you converge without any conditions, and you converge to something which is not determined in advance. It's not like in the strong law of large numbers where the average goes to a certain value independent of the experiment. In that case, depending on the experiment, you end up in different outcomes, but these outcomes are always pointer states. And if you start with at a certain position here anyway, it could be here, but it's true also here. So if you start here, well, basically there is 87. If you want to compute knowing everything that happened up to this time, let's say it's about 100, you want to know what is the probability to end in a certain state. The probability here would be about, I don't know, 0.87% for the green, and it would be around 0.15 or something like that for the black. And this one would have essentially only a few percent chances to win, but all this is random. So if you look a bit later, in fact, this one would only be 50%, and this one would be 35%, and this here, where that was negligible at that time, would be almost 30%, and you go on. But the theorem guarantees you that in the end, you will end up with something. So what I'm claiming is, if I start from the exactly same initial situations, but I do the experiment another time and thousands of other times, well, I will find this to win with a probability which is exactly equal to the value here, which is basically 0.17, and for the, I don't know, for the other colors, exactly the same. So this is really, in fact, saying that the moral of this is that doing a non-demolition measurement, so this is a non-degeneracy condition, and the result is non-degenerate measurement leads upon iteration to a standard von Neumann measurement. So really, this is an extraordinary device to look at what it means to have a larger and larger measurement apparatus. Taking a larger and larger measurement apparatus is to stop here, or to stop there, or to stop there, or whatever. And you really see that things get more and more precise. I mean, a very small measurement apparatus, you would stop here and you would say, okay, I decide that the outcome is going to be green because it's 90% and that's enough. But if you go for a longer time, you will have you will be able to be more precise. So you can. It's really something that allows you. This is really a model that allows you to look at precise finite size effects in the measurement apparatus in this game. So it's easy to convince yourself. You see, if you have only 2 results per probe, then basically the first Hilbert space you interact with is of size 2, and then of size 4, and then of size 8, and blah blah blah. And the Hilbert space gets larger and larger, and it's possible to have some arguments to say that effectively how large this amounts to have a measurement apparatus. So there was a third thing, but I have to hurry up. So I will not explain the third thing to convince you of that. What I would like to show very briefly is that in fact there is one other feature which is quite nice in these experiments, is what is the rate of convergence. And that is something that is quite easy to calculate using the recursion relations. If convergence to state, let's say alpha, well, what I claim is that q beta, for beta not equal to alpha, q beta n will behave roughly like exponential minus n s of, I have always some trouble with notations with, I'm going to tell you about relative entropies, and I never know who is who in the relative entropy, so that I would like to have correct, to have right. So where is it? Where do I define relative entropy? It's going to be S beta. I guess it's going to be S beta alpha, and S, the relative entropy S of beta with respect to alpha is simply, I want to have the signs right and all that, it's simply sum over A, P of A sigma log of P of A sigma P of A alpha. And this is always larger than 0. So this is a computation which is quite easy. If you decide that in fact this q alpha goes to 1 and the other one go to 0, then you can approximate this the recursion relation, and you do a small computation, and this is a really remarkably simple and nice result, that in fact the rate of convergence is given by a relative entropy of the probability measures that appear in the definition of the process. Okay. And so this is another feature that you expect to be true in any measurement apparatus, is that imagine that, for instance, you have an apparatus that allows you to measure, I don't know, the position of a particle. So you imagine it's a particle inside a box, and you have you want to measure the position up to a certain precision. Well, your measurement apparatus, you don't expect it to really have exactly the same accuracy for all the positions in the box. Maybe it will be very good in the center of the box, and then if the particle is close to one of the corners of the box, it will be less precise, for instance. Or whatever, if you measure a speed, for instance, if you look, well, you don't have to do quantum mechanics. If you look at your just your speedometer in your car, it doesn't have the same precision for low speeds and for high speeds. Well, exactly the same happens in quantum mechanics. I mean, measurement apparatus, they don't have uniform precision over their whole range of usability. And this is exactly what happens here. Depending on which state you end up with, the decrease of these guys is given by different numbers, and so the speed of convergence is not the same, which means that, for instance, it may be that if you to check convergence if convergence is towards alpha, you just have to do, let's say, 50 measurements to have a good confidence. However, if you want for another alpha, you might need 200 or 1000 or whatever, just because these numbers are going to be much smaller for this alpha than for the other ones. Okay, so this is so again, I claim that this builds a measurement apparatus that is has many realistic features. I mean, it shows finite size corrections. It shows dependence on outcomes in the precision. It has many nice features. So you can really use this in your mind as if you want to think about what are the finite size effects in quantum measurements. This is really an extraordinary model. Okay, I will end up on this for today. And in fact, so you could imagine that this is the end of the story, but it's not. Somehow, you might even ask, but what does this have to do with open quantum systems and thermalizations and all that? And in fact, the point is that now that we understand this, we are going to use it as a tool. And as a tool, it will allow us to observe other things. So now, for instance, imagine you take the same experiment again, but now you imagine that the cavity is less well isolated from the environment, so that, for instance, it thermalizes with an environment. And it thermalizes with an environment, and to observe the way it thermalizes, you just send these probes, and you see what goes on. And this is going to be the occasion to observe quantum jumps. You will be able, using this kind of devices, that doing non-demolition measurements on something that interacts with an environment. For instance, you will be able to see quantum jumps when the thermal bath is going to inject or remove one photon from the cavity to put it at thermal equilibrium. So this is something we shall discuss tomorrow for the last lecture. So really, these things are interesting by themselves. They are really very, very deep tests of what we understand by quantum mechanics. I mean, if you think about it, it's just incredible. And these are really thought experiments. Essentially, yeah. Yes, but you're perfectly right to be confused, because this should be a sigma. Does this help at all? Well, thank you. So it's good to be confused. When there's something wrong, it's good to be confused. Thank you. Yes. What did I want to say? Yes. For instance, you can argue that there is this famous thought experiment between Einstein and Bohr when they want to weight a box to decide whether or not there is a photon inside, and to test the uncertainty relation delta E delta T. Is larger than h bar, and this is this counterexample. If you think about it, this experiment here is really weighting this guy to decide which number of photons there are in. And in fact, this is extremely close to the setting that Einstein and Bohr had in mind. Well, it fails, of course, this experiment to violate delta E delta T equals 0, but the experiment they had in mind is essentially realized by this, in fact. It's really they are able to weight the photons inside their cavity. In fact, in the recent years, many of I would even say dream experiments for the fathers of quantum mechanics have been realized in the lab. Okay, so I close this for this morning, and so tomorrow we shall use non-demolition experiments to probe certain things in more detail, and to observe interactions. We will use it as a tool to observe interactions of a system with its environment by adding on top of the interaction with an environment non-demolition measurements. Okay, so now I switch to the second subject, and I will have to be very brief because time is running, but okay, which is the continuous time limit. It was a personal choice to decide to do almost everything in the discrete time setting, because I think things are easier to formulate. It's possible. I mean, the non-random case, I mean, we just take partial traces, is not much simpler. But as soon as you want to do experiments with real measurements and randomness, well, you can put it on a computer. It takes a few lines of code, whereas if you want to do it in the continuum, in continuous time, it's much more elaborate. So it was my choice. However, if you open books, most of them deal with the continuous time case. So for the sake of some kind of, well, completeness, of course, is not the right word, but well, just that you have seen these equations, I would like to explain you how you can get the equations in continuous time in a quite simple way. And so what we have is, you have the equation is rho n plus 1 is equal to sum over A of AA rho n AA dag. Okay. And we want to take, what is the continuous time limit? Okay. And the first step to decide that is a small lemma that I let you think about. Lemma, if rho is equal to sum over A, AA rho, AA dag, whatever rho. So I'm asking the question, sorry. I'm asking the question, when is this transformation trivial? Okay, because, well, you will see immediately, okay? So I want this to be equal to rho, whatever rho, and the answer is if and only if AA is equal to SA in HS for some SAs such that sum of the modulus squared of SA is equal to 1. So only diagonal matrices for all the AAs are going to give you a map that is trivial. So why do I give this lemma, which I let you prove it for yourself? I mean, it's not difficult. So what's the use of this lemma? It's the following, is that if I want to take the continuum limit, I would like rho n plus 1 to be close to rho n, and so my starting point will be to start from operators which are proportional to the identity. So now if I have in mind that I want to say that I take some time scale, epsilon is some time scale, small time scale, and I would like that rho t over epsilon behaves like a rho of t. Okay, that's what we have in mind when we take a continuum limit. I'm sorry, this is just to take the. I'm sorry, it's a bad habit I got from mathematicians that this guy should be an integer, so this is just the integer part of t over epsilon. It's just decoration. So I want this to be rho over t, and yes, then you see, I would like then rho n plus 1 should be equal to rho n plus epsilon times something. Okay, and if I want this, then I will say, okay, now I want my operators. AA will depend on epsilon, and if I want this to be true, when I take epsilon to be 0, I want to have rho n plus 1 is equal to rho n, whatever rho n, and so I don't have any other choice than to take these guys proportional to the identity. Okay, and so I propose to do something like I take this to be equal to the identity on HS, and then I introduce operators BA plus epsilon CA plus something which is small of order epsilon. So you could ask why do I choose this? Well, I don't have much time to explain why this is the right choice. I will try to say a few words at the end of the derivation. But anyway, so what do you have to do with that? You have to impose that AA dag of epsilon, AA dag, AA of epsilon, sum over A is equal to the identity over HS. Impose and impose no square root epsilon in rho n plus 1 minus rho n, and then compute the order epsilon. Certain observable L of rho n. compute L. Okay, and then this is quite an easy computation. I mean, you just have to write down these conditions. Of course, we make the assumption that we just have to check this relation up to order epsilon to say that in fact, then after, by adding some other terms later here, we could also correct this to get a better thing. So we check this up to little o of epsilon. And this will give us some equations among B and C. And then having no square root will give us a certain equation for B. And we go on. And this is really elementary. So I let you do it for yourself. There is no reason to spend too much time on that. This is really just a few lines. And what you will find is that, in fact, L of rho can be written as minus I H rho plus sum over A L B A of rho. And LB of rho by definition is simply B rho B dag minus 1/2 the anti-commutator B dag B rho. This is an anti-commutator. And H, so the B's are the ones you defined there, and H is by construction. This is just equal to a very simple thing that I will give you. Is defined by the following. It's defined by the following relation that. Let me state it correctly. Yes. Okay. Minus IH is equal to sum of SA CA. I guess sum over A SACA, is that correct? SA bar CA plus 1/2. Is there a 1/2? No, this there is. This is really an elementary exercise, and H, so BA whatever, and H is Hermitian. So we have to adjust the CAs. So this by construction is Hermitian, and is that? Yes, this is Hermitian, and then I have to impose that the CAs are such that this guy here is Hermitian. There is a little condition. If, how can I say? Yes. So the fact that H has to be Hermitian is a condition on that you will discover. Where is it? Probably in this relation here. If you impose this relation, you will see that H has to be Hermitian. Okay. So this is a celebrated equation. This is called. So what we end up with is. The continuous time limit is d rho over dt is equal to minus IH rho plus sum over A BA rho BA dag minus 1/2 BA dag BA rho. And so this is called the Lindblad equation. And it describes the continuous time limit of these equations. And now it turns out that, okay, so this is the continuous time limit of these equations. And now it turns out that you can derive this equation from other principles. I mean, you start immediately in continuous time, and you do a family of hypotheses on your system that essentially amount to say that the system is Markovian in continuous time, and you turn the crank, and at the end you get this equation. So it's a happy coincidence, I would say, that doing things in discrete time and taking the continuous time limit gives you exactly the same kind of result that working directly in continuous time. So in the 5 minutes that I have left, I would like to comment a little bit on my hypothesis, which was the following, that on this formula, and this is raising many questions. So I would like to spend just some time, but if you open any book on open quantum systems, at some point this will happen, and I would like to comment. So this is called the dissipator. Because if you think about it, it is related to dissipation, also to decoherence and whatever, and this is related. So this is Hamiltonian. Okay. And there is one mistake you shouldn't make, is that H does not have to coincide with the initial system Hamiltonian. And there are good reasons for so, which means that in fact, if you have a system Hamiltonian, so this maybe I should put again that this is rho s. I don't put the s all the time because this is the only one we are concerned with. But the point is, when we start the game, we have a system. It interacts with an environment. There is a Hamiltonian for the system, for the environment, and the coupling Hamiltonian. And in fact, there is no reason why in the end the H is exactly the initial H of the system. And there is one good reason for that, if only one good reason, is that if you do the equation, in fact, the equation is invariant under some kind of gauge transformation, if you want. I mean, that's maybe a big word for a simple thing I have in mind. If you change BA into BA plus I, a scalar times the identity on HS, and you change H into H minus 1/2 sum of the BA bar, BA plus BA DAG. These are, okay. So you see that it's possible to transfer some of these guys into the Hamiltonian, some combinations, and you don't see it. So there is, this H doesn't have a naive interpretation. Okay. And the other thing is, I will. Then I would like to quote the following. There is some kind of, you could say, okay, so what are conditions that say that there is a Lindbladian evolution? And this is still a subject of active research. And there is some kind of theorem that I would like to quote. It's a, how can I say? It's definitely not a theorem. There are some special cases that are theorems, but it's a moral theorem. It's the following. So you imagine that you have you have now H, which is equal to HS tensor HE, and you imagine now that you have a Hamiltonian, which is equal to HS tensor identity on HE plus a piece which describes identity on HS tensor HE, and then you add an interaction lambda V. So this is the interaction. This you call H0. Okay. And there is the following claim that if you look at rho tilde S of T, which is equal to trace over the environment of e to the I T over lambda squared times h0 e to the minus ht over lambda squared h rho of t, I guess, no, I'm sorry, rho of 0 e to the it h over lambda squared e to the minus it over lambda squared h0. And then you take the limit when lambda goes to 0. And here h depends on lambda, of course. Then this satisfies okay, so this is the formula. I hope you can read it. If not, then come after the lecture to read it. I could write it larger, sorry. But okay, so what do? We start from rho at 0 and we let it evolve according to the Hamiltonian h, as we should, but we change the time scale. So for small lambda, we are going to look at long times. So when lambda is small, imagine you start in a tensor product for the density matrix and lambda is 0, then it will remain a tensor product forever. And if lambda is small, it is going to take a lot of time to have it evolve in an appreciable way. And so you do this, but of course, in fact, there is a slight problem, is that h is going to have certain things which certain states evolving almost like h0, and these will lead to some kind of extraneous evolution. So you would like to go to the interaction representation, which means that in fact you will let it evolve, but then you will remove the evolution that would be due only to the h0 that doesn't couple the two pieces, and then you let lambda go to 0, and then this guy is going to satisfy a Lindblad equation. This is the moral theorem that justifies the use of the Lindblad equation. You can have how can I say? You can derive by hand the Lindblad equation, but then if you want to make it a theorem, well, special cases of these are known for special Hilbert spaces and blah, blah, blah. And I would just like to say that the lambda squared that appears here, lambda squared, let me put it in here, is related to the appearance of the square root of epsilon there. Okay? Because you could say that's very bizarre. I mean, if you think about it, well, I'm done, it's over, but well, let's try to argue why you would expect to have something of order square root of epsilon. And if you look at where AA comes from, with the formula I gave, you relating it to some unitary operator, you will see that it is totally crazy to have a square root of epsilon here. So I invite you to think for a few minutes what could justify that we have a square root of epsilon here. And if you don't have the square root of epsilon, you see all that remains is just Hamiltonian evolution. So the square root is crucial if you want to have some dissipation at macroscopic time scales. Okay, so I think I should stop here and maybe answer a few questions. Well, it depends very much. I mean, if I give you the AAs, and depending on the parameter, well, you see, if essentially your system is a harmonic oscillator, the only operators you have at your disposal are functions, let's say, of A and A dagger. So even more, imagine it's an even smaller system, so it's just a spin 1/2, then essentially you will have sigma plus, sigma minus, and sigma z. Sigma plus and sigma minus are fermionic creation and annihilation operators. So in the end, you're sure that it will be expressed in terms of the operators of the system. And then it depends really on the physics whether or not you will need both a sigma plus and sigma minus, or if you need sigma z on top. It depends very much. But yes, it can be related to useful operators in HS, but there is nothing telling you that it's just linear in the creation and annihilation operators. It can happen, but there is nothing telling you that this is the case in general. That answer partly your question? Okay. Yes? Yes.
So actually, framing it in a different way, one would probably say that there is no real collapse as long as the apparatus is finite.
Yes.
But what does that tell us about? I mean, I know this is very special, this unitary time evolution that we take in this case. But what does that tell us in general about the collapse of wave functions that interact with the rest of the universe? I mean, doesn't it sort of imply that there, in fact, is really no collapse of a wave function in the end, but it's always just some approximation to that?
Yes. Okay. First, I would like to make two comments about your question. The first is to answer. Yes, objectively, I would say that it's true that the total wave function collapse doesn't occur. But there is, okay, so maybe I should have insisted on that. I cheated you, of course, because, you know, proving the wave function collapse is the big goal of many people. And I don't claim I've proved the wave function collapse. Why? For a very simple reason, is that I applied the standard rules of quantum mechanics to make all the probe measurements. So I applied wave function collapse an infinite number of times there to prove that it happens once here. Okay, so I don't prove wave function collapse. I use wave function collapse for all the probes, and I deduce that it applies there. So I don't prove that. But apart from that, yes, there is no reason why there should be a perfect wave function collapse. However, you see, for the rest of the universe, the rest of the universe is so large that the time scale it takes to have somehow the collapse is small. I mean, after I don't know 1 billionth of a second, the probability that you will change your mind afterwards is 10 to the minus I don't know what. So okay. For all practical purposes, as some people say, it collapses exactly. But if you would really be able to keep very, very tiny guys, you know, this is also related to, you know, the evolution of the universe is unitary. So if you wait for a time long enough, you will come back to states which are close to the one at the, well, okay, so